Hey, this is gonna be a very quick one for today since it's pretty goddamn late. So, anyways, today we're gonna be doing last stone weight. Yeah, I know I said it solved, but solved it like quite some time ago. So I legit do not know anything about this, and I feel like it would be pretty good practice when I'm trying to learn heaps since I don't really know the syntax. So we're gonna go with that. Let's read the problem. You were given an array of integers, stones, where stone I represents the weight of the ith stone. Okay. We want to run a simulation of the stone as follows. At each step, we choose the two heaviest stones with weight x and y and smash them together. If x is equal to y, both stones are destroyed. If x is less than y, the stone of weight x is destroyed and the stone of weight. Okay, so it's just like the remainder. If they're the same, both of them are destroyed. Continue the simulation until there is no more than one stone remaining. Return the weight of the last remaining stone, or return the weight of the last remaining stone, 0 if none remain. So let's see here. It's kind of annoying that Python doesn't support a what do you call it, a max heap by default, but we'll figure out. So the example uses the max values, 6 and 2, 6 and 4, which is 2, giving us the new array. We could like basically create a max heap, push, and then pop if necessary. Although I'm thinking, is there a way to... Okay, both of them are gone. What do I do? So nothing gets pushed. If nothing remains, we return 0. So since it keeps going, we'll most likely need to use a while loop. With the condition being if there's at least 2, right? Okay. Until the last remaining stone. Okay, I can see this. So we definitely have to use a max heap, so let's do just that. We're gonna initialize it to stones, and this is how we're gonna do it like this actually. So negative stone for stone and stone. So it's gonna store the negative values, but we're gonna like basically invert it. So now every value is negative because the stone stone is like 1 and between 1 and 100. We don't have to worry about negative cases. So basically, the larger the number is, like when you pop it, it's gonna be the minimum. So we're gonna be using the logic for the like a min-heap, but by negating everything, it works the same way as a max heap. So now we heapify it. Heapify max heap. So this is our max heap now. This is where the important part begins. We have to make sure that the length of max heap is equal to 2, because if it gets less than that, then this is not possible. So heapq dot heap pop max heap, and I'm just gonna copy this line below. So this is gonna be like negative value. So can I just do negative here? And then stone 1 is going to be the greater value. So stone 1 minus stone 2 stone 1 minus stone 2 is equal to 0. We just continue because we don't add anything else. Heapq execute, then like we get the value. Actually, let's do this. Remainder, which is stone 1 minus stone 2, just to make it easier. And stone 2. And if remainder is equal to 0, we continue. But if not, that means that there is a remaining weight. And we can add that into our queue. Once again, heap push max heap remainder. Now, this is going to keep going until the length of the list is 1 or 0. Now, at the very end, we return 0 if pen max heap is 0, right? Else max heap 0. And just make sure that everything's right. So this is the negative value. This is the condition where we pop 2 and remainder. If it's 0, then nothing is there. Like it's just destroyed. Right, we got the heaviest and we made sure it's negative. I don't know if this will result in error. We might need to multiply that by 1, negative 1 if it does return error. And we push in the new remainder if it's not 0. Oh, but this will be a positive value, so let's do just that, and this should be good. Oh wait, sorry, negative max heap. Nice, and I think this should work. Wonderful. So this has a time complex. Okay, so heapifying it has a time complexity of O of n, where n is the number of stones, and then every operation like heap popping and pushing is log k, where k is the value, like the size of the max heap. So overall, it's just O of n, since O of n is just more complex than O of k. It's just like log k per loop. So it has an overall time complexity of O of n and a overall space complexity of O of n as well, where n is the of k, where k is the number of stones in it. Since that value is going to change, right? It's going to be like n initially, and it's just going to get reduced and reduce. So that's that. I'm not quite sure about the this time and space complexity. So okay, so n log n. Okay, is it n log n? This is n log n actually. What the hell is this bucket source solution? Okay, never mind. It is n log n. So n for the stones. Yes, they did a max heap approach. But why is it n log n? So this is log n. It's 2 log n, 3 log n. Okay, I'm not sure. I got the solution, but I'm not sure why the time complexity is the way that it is. So each smash is log n. Heapify is n O of n. That's not an issue. Okay, so it's because of this while loop. This runs like n times log n, so it runs n log n. The way. Space complexity is O of n, which is basically the size of a heap. It does get reduced, but it's still O of n technically, so that's what we got. And what I guess maybe we can clean this up a little bit too. Honestly, this is fine, bro. I'm not gonna lie. Yeah. I mean, it could be cleaner, sure, but it's good, I guess. This is more intuitive for me. And they're basically the same thing. Okay. I see what the point of this is, basically. Because at the end, you're gonna have 0 stones if, like, everything is destroyed. But you may have 1 stone, and if you append a 0, it'll take into account the case of having like no stones, or at least 1 stone, because it's going to be at the end, and since you're getting the first index, it's going to return that value if it exists. If not, it's going to return 0. Pretty clever way of doing it. This is fine too, though, in my opinion. May not, I think it's pretty good. It's pretty straightforward, so good job on that. That concludes it.